Hey students, welcome to the second lecture of multiple zeta values and modular forms. So in the first lecture last time we talked about the Riemann zeta function and the values of the Riemann zeta function at even integers. So in the overview here we did subsection 1.1 and we also at the end defined multiple zeta values, which we will recall in a second. And today I want to do subsection 1.2 and talk about products of the Riemann zeta values, and also I want to talk about some linear relations among these multiple zeta values. So let us recall the definition of multiple zeta value. So for an admissible index k, so an index was just a tuple of r numbers, k1 to kr, and these are positive integers, and admissible meant that the first index, k1, is greater or equal to 2. And for such an index, we defined the multiple zeta value by this iterated sum. And this condition that this index needs to be admissible was necessary for the convergence of this sum. And in the case r equals 1, this was just the Riemann zeta function evaluated at an integer. And for the case r equals 2, we denote these numbers by double zeta values. And this r is the depth, and the sum of these k's is called the weight. And one nice thing about these numbers is that they satisfy various linear relations, and the first relation appears in weight 3, and this is the first thing we want to do, namely, this was already proven by Euler. He showed that zeta 3 equals zeta 1. Which is not so obvious from the sum, because zeta 1 is something of depth 2, so it's a double sum, and zeta 3 is just a simple sum, so it's not clear why these two sums are the same. So let's prove this relation. And so there are various proofs to prove this, and we will also see later different techniques to do so. But one simple proof goes as follows. So proof. So we start with the following sum. It's a double sum, m and n, and we consider this sum, and with the same argument as before, you can show that this sum is absolute convergent, and the idea is now to evaluate this sum in two different ways. So one way is that we can write this sum as follows. So it's n squared, and this you can see if you just well, it's basically partial fraction expansion of this expression here, and since this is absolutely convergent, we can now take first the sum over m. And we see here that if we take the sum over m first, that this is a telescoping sum, meaning that a lot of things cancel out here. So outside we have the sum over n. And inside, the only part which remains in this sum here is the case where this m goes from 1 to n, because all other parts cancel out here. But this is almost the definition of zeta 1, except that this m here can also be equal to n. So in this case, when m equals n, then we just have n cubed here. So this is just zeta of 3 plus, and then there's a case where this m is strictly smaller than n, and then this is just a definition of the double zeta value, zeta 1. So here's a 2 and there's a 1. So the first evaluation of this sum is that this equals zeta 3 plus zeta 1. And another way is we can write the sum as follows. So this is And again, you see that this is the same by just bringing this on the same denominator. And then we can split the sum up into this part and into this part. So the first sum is just this, plus, and the second part is this. So it's basically the same sum, where we just rename m and n, and this, so here, this is strictly larger than this, so we could rewrite it as an ordered sum, and these two sums are the same, and what this just is, this is just the definition of zeta to 1, and we have it twice, so this is 2 times zeta to 1, and therefore 2 times zeta to 1 equals zeta 3 plus zeta to 1, which then implies that zeta 3 equals zeta to 1. So this is a simple proof, and this gives the first linear relation among these numbers. But a more systematic way to prove linear relations among these numbers is by the so-called double-shuffle relations, which I now want to explain in the simplest case. And the basic idea is that we will get two different expressions for the product of multiple zeta values, and then compare these two expressions, and this will give a linear relation. So in the definition, before we defined multiple zeta values, we considered the product of two Riemann zeta values, and then we thought that if I multiply two Riemann zeta values, I could write it as two double zeta values plus a single zeta value, and this was just a simple simple combinatorial argument splitting up this sum into three parts, and then we got this expression. And this is called the so-called Staffel product. But there's another way to express this product of two Riemann zeta values, which is given by this proposition. So if k1 and k2 are greater or equal to 2, so these two numbers make sense, we can also write this as this linear combination of double zeta values. And this is called the shuffle product. And this is this is the first exercise showing that this equality holds. And one way to prove this, how we can do it in the exercise, is, so the proof idea is use partial fraction decomposition to get this equality. And so let's do one example. So for example, let's say k1 is 2 and k3 is 3, then the Staffel product is zeta 2 times zeta 3 is zeta 2 3 plus zeta 3 2 plus zeta 5. And the shuffle product, so this formula here, if you would work this out, you would see that this product here is zeta 2 3 plus 3 times zeta 3 2 plus 6 times zeta 4 1. And in particular, we see, because the products are the same, we also see that these right-hand sides are the same, and this gives a linear relation. And in this case, we get that zeta 5 is 2 times zeta 3 2 plus 6 times zeta 4 1. And this type of relation, so this is called double shuffle relation. Because it comes from this comparing the Staffel product and the shuffle product. And Now you might ask, why stuffle and shuffle? So these are quite strange words. So the stuffle product, what you do is you take these indices and you first shuffle them, and now there are, as far as I know, two explanations for the word stuffle. So one explanation is that you shuffle these indices and then there's some extra stuff, and another explanation is that to stuff means to put something into one place. So here this K1 and K2 get stuffed into one place. And this is why people call this a stuffle product, but this is also sometimes called the harmonic product, because it comes from the definition of multiple zeta waves as a harmonic sum. But then there's also this shuffle product with this fancy formula, and in the exercise you prove this formula by using a partial fraction expansion. But this has a nice combinatorial explanation, and the idea is what we will see in section 2 when we discuss the algebraic setup and iterated integral expressions. So there will be an iterated integral expression for these multiple zeta waves, and if we multiply two of these integrals we can explain these formulas. But there's also a purely combinatorial idea behind this. So the idea is that multiple zeta values can be seen as decks of cards. So a multiple zeta value is a deck of cards where we just have two types of cards, a red card and blue cards. And then, so if I have a deck of cards, by which I mean, for example, I have some blue cards, and on the bottom I have a red card, and if I have in total K1 cards, then this corresponds to zeta K1, and if I have K2 minus 1 blue cards and one red card, so here this is K2, then this should correspond to zeta K2. And what we want to do now is, now the reason why this is called the shuffle product, we want to shuffle these two decks in the, so this is the shuffle product. So you take these two decks and shuffle them into each other, and then you ask for the possible outcome of this shuffling. So in this case I have two red cards and some blue cards. So the possible outcome, if I do a shuffling like this, is that I will have a deck of cards with some blue cards on top. Then at some point I will have a red card. Then again some blue cards. And on the bottom will be a red card. And now we want to ask ourselves, how many possible ways are there such that the first blue and the red card I have J cards, and the rest is, well, in total I have K plus K1 plus K2 cards, so this is K1 plus K2 minus J. So J is the position of the first red card. And also we see that the red card needs to be on the bottom, because if I shuffle these two cards, then at least one of these red cards is on the bottom. And this deck of cards now corresponds to this multiple zeta value. And in general, if I have zeta K1 up to Kr, I always have the first red card is at position K1, and then after K2 I have the next red card, and so on. And now, if I shuffle these two decks of cards, what are the possible ways to get exactly this deck of cards where the first red card is at position J? And the answer is, well, the first red card here could be either this red card or it could be this red card. So let's assume, that this is actually this red card coming from the zeta K1. How many ways are there that this can happen? Well, if this is the red card of this deck, then all these blue cards, these k1 minus 1, need to be here. In all the possible ways, because I cannot distinguish between two blue cards, I need to ask myself, how many ways can I put these k minus 1 cards into these j minus 1 blue cards? Well, and the answer is, of course, j minus 1 choose k minus 1. Oh, maybe this I should make green then. So the answer is j minus 1, k1 minus 1. But then there's also the possibility that the first red card is this red card coming from this deck, and then I ask myself, how many possible ways are there to put these k2 minus 1 blue cards into these j minus 1 blue cards? Well, and the answer is j minus k2 minus 1. So this here gives a number of ways to get this exact deck when I shuffle these two cards together. And you see this is exactly the formula we have here. And why this works we will see in section 2, but I can just tell you now that this will work in general. So always when you have two multiple zeta bays of arbitrary depths and you code them into cards and then ask yourself what's the possible ways of shuffling these together, then you get another expression for the product besides the shuffle product. And this is why this product is called the shuffle product, because it somehow corresponds to shuffling something. And later these two different kinds of cards will just correspond to two different differential forms in our iterated integral expression. Okay. So now we want to consider the space of multiple zeta values. And for this we define two things. So by this Z we define the space spanned by all multiple zeta values. So we take zeta k, where k is an admissible index. So notice that because the empty index is also in there, we have that q is also contained in the space Z. And then a subspace for every k greater or equal to 0, we define zk to be the space spanned by just multiple zeta values where the index has weight k. And for example, Z3, so Z3 is a span of zeta 3 and zeta 2, 1. But we already saw that zeta 2, 1 equals zeta 3, so this is just the one-dimensional vector space spanned by zeta 3. And these products we discussed before, this shuffle and stuffle product, we will make sense of this for arbitrary depths in the next section, and we will see that this space Z is actually closed under multiplication, and it's a Q subalgebra of R, and we also have that if I multiply a multi-zeta of weight k1 with a multi-zeta of weight k2, then this can be written as a linear combination of multi-zetas of weight k1 plus k2. And this is just a generalization of this idea here, because the way we proved this was just splitting up the summation in this product here, and this works in arbitrary depths, and this we will make precise later, but maybe this proposition you can already believe now because it's quite simple to prove. And all relations we saw so far, so zeta 3 equals zeta 2, 1, and also this relation here. So here in this relation, zeta 5, zeta 3, 2, and zeta 4, 1, all these multiple zeta values have the same weight, so in this case they have weight 5. And also in this case here, every multiple zeta value has a weight k1 plus k2, so this just gives relations among multiple zeta values of the same weight. And this seems to be true in general, that we actually do not have any relations among multiple zeta values of different weight. So this is one of the main conjectures in this field, namely that this space Z is created by weight, meaning that the set can be written as a direct sum of these zk's, meaning we do not have any linear relations among multiple zeta waves of different weights. And in particular, this implies that all multiple zeta waves, so if this conjecture would be true, this would imply that all multiple zeta waves are transcendental, which is also part of the exercises. Okay, so now, here in this example we see Z3, the dimension of this space, for example, is 1. So it has two generators, but there's a relation among these generators, and the dimension of this is 3. So you might ask, what is the dimension of this zk in general? So you can maybe do some computer experiments to get linear relations, or you can prove linear relations, and then you can get a conjecture. So, and before we state the main conjecture on the dimension of zk, we want to introduce the following numbers. So we want to define the generating series of these numbers dk by this rational function. So if you would work this out, you see, for example, that d0 is 1, d1 is 0, so this starts with 1 plus 0 times x plus x squared, so you will see that d2 is 1, and then because this is given by this rational function, and if you would multiply this over here, you will see that this dk, that they satisfy some recursion, and the recursion is given as follows, saying that dk equals dk minus 2 plus dk minus 3, and this works when k is greater or equal to 3. So for example, d3 is 0 plus 1, so this is 1, d4 is 2 plus 0, so it's also 1, and d5 is 1 plus 1, so this is 2, and so on. So these are numbers which you can write down explicitly, and then the main conjecture due to Zagier is that the dimension of zk is actually given by these numbers dk. So for example, d3 is 1, so the dimension of z3 should be 1, as we saw before. And here is some table with these numbers. So let me put this here maybe. So here you see the numbers in dk, and here you see the number of the number of admissible indices. So for example, in weight 3 we have 2 admissible indices. So this is 2, 1, and 3. But they satisfied one relation, so the dimension is 1. And here in weight 4 we have 4 generators, or 4 admissible indices. So we have 4, 2, 2, 3, 1, and 2, 1, 1. And this conjecture predicts that the dimension of Z4 is actually just 1, meaning that all the corresponding zeta waves here are just a multiple of each other. And for example, one example we will see, which generalizes this relation we already proved, is that zeta 2, 1, 1 is actually just zeta 4. And in general, this will be an example of the so-called duality relation, that zeta 2, 1, 1, 1, 1, 1 is always equals zeta k. But also zeta 2, 2 and zeta 3, 1 is also a multiple of zeta 4. And we get the upper bound 1 here for the dimension. And so this conjecture is an open conjecture, because a lower bound for this conjecture is really hard. So actually we cannot give any lower bound except for 1 for any of these weights. So we cannot prove, for example, here in weight 5, we cannot prove that this dimension of Z5 is actually 2, we can count relations and then show that the upper bound is given by 2, but the lower bound, for this you would need to prove that, for example, zeta 5 and zeta 2, 3 are linearly independent, which is impossible so far. But a deep result, due to Terasoma, Deligne, and Goncharov, states that this number dk always gives an upper bound for the dimension of zk. And this uses some deep algebraic geometry and mixed state motifs, and is quite complicated, but and so far there's no somehow, so to say, easy proof of this fact. So one stupid way to prove this would be to just count a certain number of relations and then give this upper bounds. But these proofs all depend on some geometric methods, and this is a quite deep result, this upper bound. But for a lower bound, we so far don't really have any results. Okay, so the next conjecture I want to mention is due to Hoffman. Namely, he states, or he conjectures, that there's actually an explicit basis for these zk's. And his conjecture states that this set, so this is this, so for fixed weight k, the set of all multiple zeta values, where of weight k, meaning the sum of the k's is k, where all of these k's are either 2 or 3, that they form a basis of the space zk. So in other words, for example, zeta 4 should be some multiple of zeta 2, 2, and zeta 5 should be expressible as zeta 2, 3 and zeta 3, 2. And for example, zeta 2, 1 we already saw is zeta 3. And at this point, what I want to show is actually, so how did Zagi come up with this conjecture here? So what he did is computer experiments, and I want to show you a little bit how to do this. So there's a program called PariGP, and you can find a link. You can just Google this, or you can find a link in the lecture notes. And here on my laptop, let me show you this. So here you see, if you download PariGP, so this is now on a Mac, and if you install it, you can just start it with GP. And in PariGP, these multiple zeta values are implemented, and also, for example, the Riemann zeta function is just zeta. So if you type in zeta 2, then you get this number, and pi is given by pi, and pi squared over 6 gives the same number. So this is the equality that zeta 2 equals pi squared over 6. And multiple zeta values are defined like this. So zeta mult, and then, so this is a function, and then you give this some array. An array in Pari is given by these brackets. So for example, zeta mult 2, 1 is this, and this should equal zeta 3. So now, let's check this one here. So I want to know the Hoffman conjecture. How do I get this number? So I want to see if there's a relation among zeta 4 and zeta 2, 2. And for this, there's a command, lindep, for linearly independence. And this I can give an array of numbers, and then he looks for linear combination with integer coefficients. So in this case, I want zeta 4 and zeta mult, so multiple zeta value 2, 2. And this now tells me that, so this result, the statement of this result is that minus 3 times zeta 4 plus 4 times zeta 2, 2 equals 0. So this always gives me the coefficient of a linear combination of the input, which is 0. So in other words, this number here I'm looking for is 3, of course the other way around. It's 4 over 3. So 4/3 times zeta mod 2 should be zeta 4. And this works with more than just two input things here. So for example, zeta 5 and zeta 2, 3 and zeta mod 3, 2. So this now looks for a linear combination among these three values. And we get this linear combination, and in particular, this says that, so this says minus 5 times zeta 5 plus 6 times zeta 2, 3 plus 4 times zeta 3, 2 equals 0. So in particular, zeta 5 can be written as a linear combination of zeta 3, 2 and zeta 2, 3, which somehow supports this conjecture here, stating that these multiple zeta waves where the entries are just 2 and 3s give a basis of the space zk. And this we actually know due to a result of Brown. We know that these so-called Hoffman elements, that they actually generate the space of multiple zeta values. So the space zk is actually generated by these multiple zeta values with entries just 2 and 3. But what we don't know is if these elements are linearly independent, and this is the open part of this conjecture due to Hoffman. And in the lecture notes you can also find a little bit more comments on how to find linear relations using Paris-Dupuy, and also some more comments on these conjectures. And in the next lecture we will discuss the first connection of modular forms to multiple zeta values, and also give a hint what's the relationship among linear relations among double zeta values and cusp forms, which are a special type of modular forms. See you then.